Hi, everybody. So, we are going to be talking about spherical geometry today. Now, everything you've learned and everything you will learn in your mathematical career in high school, at least, will be based upon Euclidean geometry. But we are going to be talking about spherical geometry. So, that's where geometry is occurring, and that plane is the surface of a sphere. Whereas on Euclidean, it's a flat surface. So here are what the undefined terms on a circle look like, or I'm sorry, on a sphere look like. So the point would be the same as it is in Euclidean geometry, and let me go ahead and write that in there. There we go. So this right here, point P, these are color coordinated for y'all. This is would be point P or point Q. Same thing, one capital letter. A line segment is going to be an arc of a great circle. So the shortest distance between 2 points is a line segment, but in a sphere, it is considered an arc. This is why we're relating it so closely to circles, because you work with minor arcs and major arcs. So that minor arc especially typically is going to be the shortest segment between 2 points. Now, I keep saying great circle. A great circle is going to be, let's see if it'll let us, yay, this thing right here. I'm going to write that in black. So that great circle that you see, that is highlighted in purple right there. That is when you've got the sphere and a plane, okay, and they're intersecting. Pretty much when you cut an orange down the middle, down the center, you get a big circle. That is your great circle. That is considered a line in spherical geometry. So you could label it a couple of different ways. You could do line. Ooh, sorry about that. You could do line PQ, just like we've been doing, or you can call it great circle PQ. You could also call it line U or line V by using only one letter, and those letters are just, they're not points. They're just there. They happen to be coinciding there. Or you could call it great circle U or great circle V. Great circles, by the way, are used by pilots to navigate Earth. And that's how they determine where the shortest path is between 2 points. Now, this is a huge sphere with 3 different great circles, and there are going to be so many different great circles because there are so many ways that you can cut an orange down the middle. So two lines, containing point R. So there's point R, and we've got this big old line, and we've got this big old line. So thinking about the different ways that you could name them. And so I have lines GP, so that's using these 2 points, and lines MQ, right here, are lines on sphere F, see that letter F, that contain point R. You could also call it line MJ, you could call it line GP, which we already did. You could call it line GR, GK, GS. So a lot of different names, as long as you're using those 2 capital letters, if there's not a lowercase letter to name that line. Now, a segment containing point K, we've got right here, PS. This arc right here is containing PS. That is the shortest one. Now, there are quite a lot of different pairs here. So that is minor arc PS. You could have also used major arc GPS right here, and that is totally fine. You could have seen arc JK, but we want it to be containing, not necessarily ending. So line JM or arc JM. In this case, you could even title it a major arc because it is going to be half of that sphere. And there are so many different more. In class, I think we came up with like 4 or 5 of them. And then the next one is a triangle. The triangle is going to be a whole lot easier to see for most people. And you'll notice it's kind of, it's a little fluffy. So triangle RQP right here. Okay, so it looks like they're not completely straight right there, those connections, and they look a little bit more curved. That makes sense because line segments are arcs on spheres. All right, we'll talk more about the triangles because there was a special case about this. And that's because it's all related to this concept, and we want to build on that before we go to that postulate. So, Euclidean or not. Now, Euclidean geometry is what you've been doing and what you will most probably continue to do after this and the rest of your high school career. It's the geometry that we have been using, that's been in use for over 2,000 years, right? Whereas non-Euclidean geometry, which is spherical geometry, it's one of them, okay, is when at least one of the postulates of Euclidean geometry fails. Now, we've already seen some of those postulates fail. And you might have even noticed being like, well, things can't be this. And we'll talk soon. So, we're going to look at this segment right here, the statement. Through any 2 points, there is exactly one segment. So, if we were working in Euclidean geometry, it would look something like this. Straight line segment. I know I get on to you guys about saying straight, but for the purpose of this conversation, we'll talk about it, especially because we're working with 2 different types of geometry. On a sphere, you'll notice that this is not a line segment, it is a arc. And remember, there are 2 types of arc. You can have either you can either have minor arcs or major arcs. So there are 2 arcs containing both points. Through any 2 points, there are 2 arcs. Because you've got that minor arc and you've got that major arc. Now that I can talk again. All right, now a line segment is the shortest path between 2 points. That is true in Euclidean geometry. And the way that you rephrase it for spherical, which we put on the front of our notes, is that an arc, and I want to put that it's of a great circle, is the shortest path between 2 points. Not just any random arc. So I can't be one of those people that's cutting off just this tiny piece of an orange. First off, you're going to get weird looks if you do that. Second of all, that's not going to be as short. That great circle ensures that we're going to have the shortest path between 2 points. So here is the parallel postulate, and I'm so sorry that that's off. Okay, so the parallel postulate on spherical geometry is that through a point not on a line, there is no line parallel to the given line. There literally isn't. Because lines are great circles, and you can cut that orange through the center multiple different ways. So, since lines are great circles, in spherical geometry, 2 lines are always going to intersect. And in fact, any 2 lines on a sphere intersect at 2 points. That is always true. And we saw that in our previous example that we worked through together. Now, here's another postulate that breaks. We know that in the geometry we worked with, a triangle, the angle sum of it is 180 degrees exactly. Well, that's not true in spherical geometry. So the sum of the interior angles of a triangle on a plane, that is always going to be more than 180 and less than 540. So it cannot equal 180 and be considered a triangle in spherical geometry. It has to be more than 180 and less than 540. And that's because it's being created by 3 arcs that lie on different great circles. Right? Now, since the sides of a, so sorry this is happening, since the sides of a triangle in a spherical geometry are arcs, the sum of the measures of the interior angles is always more than 180 and less than 540. Exactly what we just talked about. And here's how you would write it as an inequality. Notice there's no equal to sign on either of those inequalities because it does not include those numbers. A triangle that is 540 degrees on the interior is not considered a triangle in spherical geometry nor in Euclidean geometry. So let's go through some examples. Okay, so let's talk about this one first. In Euclidean geometry, how many lines are parallel to a line through a point P that does not lie on the line? So you've got some line here and point P here. You want to create a parallel line to line O. Well, in this case, and if you only want it through point P, then you've only got one line. If, say, point P didn't exist, then of course you could draw an infinite number of lines. Now, that's based upon the parallel postulate in Euclidean geometry. But that same thing we know is not true in spherical geometry. So say you've got point M here, okay? There's no way that you're going to be able to create a great circle, which is a line on here that does not intersect. Because you would have, say, this great circle. That wouldn't work. Now, if you try to say, well, I can just cut it here, that's not a great circle because it doesn't go through the center of your sphere. All right, so examples 2 and 3, they are much easier. A and B, you're just adding up. So A, you're going to add up 121, 23, and 105, and you should get 249 degrees. Don't forget that degree symbol. Triangle B, you've got these right angles, they still mean 90. Okay, that still means the exact same thing. We're just using that. And so 90 plus 90 plus 80 is going to get us 260 degrees. And those are both triangles in spherical geometry. Now, in this situation, in example 3, I've given you 3 different angles of a triangle, and we have to determine if it's an Euclidean, spherical, or neither of the geometries. So the first step would be to add up the numbers, okay, and now determine which one does it fall under. Is it equal to 180 degrees exactly? Is it between 180 and 540? Or is it less than 180? Oops. And more than 540? Well, in this case, this is going to fall under spherical because it's between 180 and 540. The next one we get 155. Well, automatically it's not Euclidean because it doesn't meet 180 degrees exactly. Because it's less than 180, it can't be spherical either. So this is neither of the 2 geometries that you are aware of. Yes, there are more geometries. No, we will not talk about them. You're okay. All right, this last one, 63 plus 63 plus 54, that should get you 180 and not 1180 degrees, but 180 degrees. And because it's exactly 180 degrees, we know that that is a triangle in Euclidean because that's the geometry we work in typically in our high school career. All right, so that is your quick glimpse into spherical geometry. Hope you enjoyed.